So good afternoon to everybody. Sorry not to being here. So I will show you how it's possible to fit emission line of AGN and of course the host galaxy with CIGALE. So the goal of this is to derive the parameters which are driving the galaxy evolution. And to do this, we will use the galaxy spectral energy distribution with all its components, the stars, the dust, and the gas, and possibly the AGN. So we will combine spectroscopy and photometric data to make a fit and to derive this parameter, or if you do not have observation, we will generate synthetic spectra to predict observation. So because galaxy is a very complex, inhomogeneous medium, we will have to model, and sometimes, of course, at this high redshift, we don't have the spatial resolution, we'll have to model the different components. So the first component is the host galaxy itself. So you have old stars in red, and you have a young star in blue, where you have an H2 region. So to model this H2 region, we need a shape of the radiation field, a shape and an intensity, and we need a description of the ISM with the density and the metallicity. And then we will use the cloudy radiative transfer code to generate a library of spectra in green. So a library of spectra depending on a set of parameters that we will put in the CIGALE code so we can fit both the photometry and the spectroscopy, and from this to retrieve the parameters of the ISM. So the photoionization radiation field has a shape, which is depending on the single stellar population, which is depending on the initial mass function and the star formation history, and the amount of binary stars. And the intensity is given by the number of Lyman photons. To model the ISM, we will use the local galactic concordance model. We will give you abundances with respect to oxygen. So the zeta parameter is the metallicity, so the oxygen. And we will use observation of 33 nearby stars to have a prescription for helium, carbon, and nitrogen abundance with respect to oxygen. So having that, we can use Cloudy to synthesize the library of spectra and to put in CIGALE, which is a SED thinking code, which can do Bayesian analysis. And when we can either produce synthetic spectra, or if we have data, so here is a cross-match between the Cosmos catalog and the FMOS catalog, where we have line emission for H alpha and oxygen. If we do that, we can compare observation in X scale and modeling, and we can see that for both the photometry and the spectroscopy, we can reproduce pretty well the observations. And if we use the standard BPT diagram with our catalog of observation, we can see that we can cover all the observations which are in the galaxy region. Okay. Now, the second component, which is the PDR, which is representing the denser medium of the ISM. So if we look at the PDR structure, you can see that some lines are generated. So this is the H+ region, this is the PDR, and this is the molecular zone. You can see that some lines are generated in the PDR. So in red, you have the lines which are generated in the H+ region. In blue, you have the lines which are generated in the PDR. And because all these lines are attenuated, so these are the green lines. So the red line are attenuated and becoming the green line. So to model this, we need to model these three components. So we have lines which are produced in the H+ region and are attenuated. Modulo a covering factor, which is representing the porosity or the clumpiness of the ISM. And then we have lines which are produced in the H+ region and attenuated and extended. And we have lines which are produced in the PDR. So then we can combine the three of these lines. So we would make the assumption that because of the temperature, we have no dust in the H+ region and we have dust in the PDR. And you see that one member of this equation has an attenuation law. So we can play with a different attenuation law. And one term as an extension law. So the extension law, we have to derive it, and we will take an AV of 1, which is typical of a galaxy. So we use cloudy to perform radiative transfer, and we derive our own extinction law. Then we have all the line, and we can try to find line ratio which are tracing a component. So for example, here, ionization parameters. So we are looking for something which is a line ratio is strongly varying with the parameter, but ideally weakly varying with other parameter like the density or the metallicity, and compare to the observation in gray. So we do that for log U. We can do that for metallicity. So you see it's more complicated, but because you have correlation between the metallicity and the ionization parameter. We can do that for the density and for the covering factor. So you see that you have a lot of correlation. So of course you will need a lot of line ratio if you want to lift this correlation. One alternative is to use an optical diagram. So an optical diagram is a line ratio versus a line ratio. So you can see the trend as a function of the different parameters. And depending on the position of the galaxy on this diagram, you can have an idea of the value of the parameters. And because of the correlation, you better have different diagrams. Okay, so as a conclusion, we isolated useful tracer to derive the parameters. And we can jump on the third component, which is the AGN. So the AGN spectra is very depending on the viewing angle. So if you have a viewing angle, small viewing angle, you will see both the narrow line region and the broad line region. And so the safer one quasar. And if you have a large viewing angle, you will only see the broadline region, safer 2. So we have a model where we have these geometry dependencies. So the black hole, the accretion disk, the corona, the torus of dust, the broadline region, the narrow line region, and all around the polar dust. So we have the jet. We do not have the jet in the moment in our model. All right, so first component is the incident radiation field. So the corona region is modeled with an exponential law. So we have the gamma index and the energy cut. And then the accretion disk is modeled with a series of broken power law, which can be modulated somehow. So we have 3 parameters to shape this incident radiation field from the black hole. And the intensity is also always modeled with a radiation parameter. So ISM is modeled on the same way using the local galactic concordance model, and with a difference, but we will consider a standard depletion in the narrow line region, and also because of the temperature, we will consider that in the broad line region, all the grains are sublimated. But both the narrow line and the broad line region are affected by polar dust and undergo some attenuation. So again, we use a cloudy to process radiative transfer and to generate a library of spectra depending on these different parameters. So we have a nebular AGN module in CIGALE that we will benchmark. So first we will benchmark on a composite spectrum of 2000 quasar. So you can see that we can reproduce very well the lines in the visible. We can reproduce fairly well, some difficulty, but fairly well line in the UV. And what is interesting is if we compare the line flux for several lines, so these are the observed flux. So this is in a catalog which is cross-match with the XMM, so it's X-ray selected. So we compare the observation with the modeling, And we apply to this model different attenuation law. So first, you can see that we can cover all the observation. But what is interesting, if you look at the Balmer decrement, so this is a Balmer decrement of the model, and then we apply different attenuation law, and then you can see that just playing with the attenuation law, we can reproduce the observation, which show the importance of the polar dust. Then we compare observation to our modeling with or without, so with in red and without in blue, without applying AGN spectra. So you see in red that it's much, adding the line emission from the AGN reproduce much better the observations. So again, we can benchmark the module using a BPT diagram. So you see that this time we can reproduce both the galaxy in the starburst region and the galaxy in the AGN region. So all the X-ray selected sample are in this region and we can reproduce them. And of course, this has the advantage that depending on the location of the galaxy, you can have an idea of the value of the different parameters. Then we perform a line sensitivity analysis. So we try to find which line is a good tracer of which parameter. So a strong tracer is of course intense, so we can observe it, but also there's a strong variation with the parameters. But to do this, we need a lot of line and we need a lot of spectra. So fortunately, PFS is now giving thousands and thousands of spectra. So we are presently integrating the different bands and determine the redshift. So very soon we will have a lot of spectra. So both on PFS and moons, because now moons is in Chile and is being commissioned. So we will get the science observation probably at the end of the summer, and we will get a lot of spectra to make SED fitting with CIGALE. So thank you for your attention.
Thank you, Patrice. You are perfectly on time. We have enough We have enough time for questions. Any question from the audience or the chat? I have a question about how, I mean, this looks like a very complicated model. So yes. How do you fit the data? Do you run a grid of parameters, or basically you have it already and you just have to locate the points in your diagrams and voila?
It can be both. It can be both actually. So these are typical data. So you integrate the bands and you can, I mean, you know the bands, right? So you can put them in a diagram, or you can perform a full SED fitting, and which is more powerful because you optimize both the photometry, so all the stellar mass, the star formation, and all these parameters you can optimize on the continuum, and add the spectroscopy fitting. So it's both photometry and spectroscopy fitting. So you can, you can have all the parameters plus the parameter of the ISM. So you can do both actually.